Hi everyone, we're back to right triangle trig. We ended last time with the ancient curse, Sohcahtoa, which reminded us that sine of theta was opposite over hypotenuse, cosine of theta was adjacent over hypotenuse, and tangent of theta was opposite over adjacent. Where this is theta, this is the opposite side, this is the adjacent side, and this longest side is hypotenuse. Now try to remember from your trig class, what was the reciprocal of sine of theta? We're going to get the three reciprocal functions for these, and we're going to get the reciprocal identities. The first of 5 groups of identities we'll discuss in chapter 4. What's the reciprocal of sine of theta? What is 1 over sine of theta? Many of you may have said secant of theta, and you would be wrong. The reciprocal of sine of theta is cosecant of theta, and a lot of people forget that. The reciprocal identities. This is how we'll define these 3 additional trig functions. Cosecant of theta, again, parentheses are nice. Cosecant of theta is the reciprocal of sine of theta. Secant of theta is the reciprocal of cosine of theta. And cotangent of theta, conveniently, is the reciprocal of tangent of theta. But remember, the reciprocal of sine of theta is not secant of theta, it's cosecant of theta. Do not mix these up. It's kind of like when we had horizontal translations, where we were doing minus versus plus, shifting right versus left. It's the opposite from what you expect. You might think the reciprocal of sine of theta is secant of theta, but you'd be wrong. It's cosecant of theta. That's the reciprocal of sine of theta. As it turns out, this will help us with the Pythagorean identities later on. So it's helpful to remember that the cosecant of theta is the reciprocal of sine of theta. The secant of theta, on the other hand, is the reciprocal of cosine of theta. And as expected, the cotangent of theta is the reciprocal of tangent of theta. I think it's helpful to think of these in terms of reciprocals. I don't think that cho, sha, cow will help us so much, as Sohcahtoa did. Oh, one other thing. If theta is quadrantal, like 0, pi over 2, pi, and so forth, then it's possible that sine, cosine, or tangent could be 0, in which case these could be undefined. In fact, tangent itself could be undefined. Now, here's something that's kind of weird. In basic trig, we can think of 0 and undefined as reciprocals of each other. Now, again, this will not happen if theta is acute, but this can happen if theta is quadrantal, like 0, pi over 2, pi, or so forth. So, for example, if sine of theta is 0, then cosecant of theta will be undefined. So your algebra teacher would agree that the reciprocal of 0 is undefined. There's no problem there. But here's something that might sound weird to your algebra teacher. Let's say the tangent of theta is undefined. Then for that value of theta, cotangent of theta will be 0. So when it comes to basic trig, you can informally say that in basic examples, the reciprocal of undefined is 0. Now, you can't say that formally, and your algebra teacher would freak out. So don't tell your algebra teacher that the reciprocal of undefined is 0. That's not a proper thing to say. But for all practical purposes, hey, if tangent of theta, say, is undefined, then yes, cotangent of theta will be 0. So we can treat 0 and undefined as reciprocals informally in basic trig. All right. Now, in addition to the reciprocal identities, the second group of identities we'll look at will be the quotient identities. We have 2 of these. Tangent of theta is sine of theta over cosine of theta. It's the quotient of these 2 basic trig functions of theta. Cotangent of theta is the reciprocal, so you just flip this fraction. Cotangent of theta is going to be, you flip these guys, cosine of theta over sine of theta. So it's helpful to remember tangent of theta is sine of theta over cosine of theta. For cotangent of theta, you take the reciprocal. Now, why is this consistent with Sohcahtoa? So here's some very informal algebra. So let's assume theta is acute for now. Sine of theta, so, is opposite over hypotenuse. Cosine of theta, ka, is adjacent over hypotenuse. Now, if you take this compound fraction, and if you multiply by hypotenuse over hypotenuse on top and bottom, you basically cancel out the hypotenuses. The two little bottoms disappear. They cancel out. And we end up with opposite over adjacent, which was tangent of theta. That's TOA. Tangent of theta is opposite over adjacent. So the quotient identity here is reciprocal with Sohcahtoa. You could do something similar with cotangent of theta and its identity. So the reciprocal identities and the quotient identities make up our first two blocks of trig identities. Our third block will be the cofunction identities, which we'll discuss soon enough. And then later on, we'll have the Pythagorean and even odd identities. Speaking of Pythagorean, let's talk about the Pythagorean Theorem, which will be the foundation for the Pythagorean identities. All right, this should look familiar. The Pythagorean Theorem. There are literally hundreds of proofs for the Pythagorean Theorem. Actually, we don't think that Pythagoras himself, the ancient Greek mathematician, devised one for himself. He basically stole other people's credit for this. The Pythagorean Theorem. Now, actually, President James Garfield came up with a proof. That's not why they shot him, but he did come up with a proof. He was a very smart man. Okay, he was not shot by a jealous mathematician. All right, the Pythagorean Theorem. So let's say that the opposite side is A in length, the adjacent side is B in length, the hypotenuse is C in length. This should look familiar. A squared plus B squared equals C squared, the Pythagorean Theorem. The square of the hypotenuse equals the sum of the squares of the other two sides. This is famously misstated in The Wizard of Oz and The Simpsons. Okay. Now, when you apply the Pythagorean Theorem, it's helpful to remember the Pythagorean triples. In fact, if you know these Pythagorean triples, you won't have to crank through this. The Pythagorean triples are a set of three integers that can represent the side lengths of a right triangle. The most famous one looks like this. So let's say that the units are in meters, let's say, some common unit. Let's say that this side length is 3 meters. I'll put the unit, 3 meters. Let's say this side length is 4 meters. Notice these are the two legs of a right triangle. If the two legs of a right triangle have lengths 3 meters and 4 meters, we know that the length of the hypotenuse, or just the hypotenuse, is going to be 5 meters, because we know this Pythagorean triple, 3, 4, 5. That's because 3 squared plus 4 squared equals 5 squared. 9 plus 16 equals 25. In fact, proofs often involve physical squares. The area of this square plus the area of this square equals the area of this square. 9 plus 16 equals 25. The sum of the squares of the two legs equals the square of the hypotenuse. Now, let's say that, now before we go on, I want to point something out. I'll go ahead and erase these. Again, the actual squares are often used in proofs. What if instead we had this? What if we had the 4 meters? What if we had the 4 meters on the hypotenuse? Does that mean that this side length here is going to be 5 meters? Do we automatically put 5 meters on the missing side? And the answer is no. Why not? The hypotenuse is supposed to be what? What side? The longest side of the right triangle. So there's no way that you can have a triangle like this where 4 meters is the hypotenuse and yet 5 meters is a longer leg. This cannot happen. So if you apply this 3, 4, 5 Pythagorean triple, make sure not just that you're dealing with a common unit, but make sure that the longest side length is in fact the hypotenuse, not a leg. If you have a situation like this, then sorry, but you're pretty much going to have to crank through this equation. Okay, now there are other famous Pythagorean triples besides 3, 4, 5. We have 5, 12, 13. If this is 5 meters, and if this is 12 meters, then this is 13 meters on the hypotenuse. And that's because 25, the square, plus 144 equals 169. Also, the third famous Pythagorean triple is 8, 5, 17. If 8 is here and 15 is here, then this has to be 17. And that's because 64 plus 225 is 289. Now, in fact, number theory tells us that there are infinitely many of these primitive Pythagorean triples. I say primitive because you can get multiples of these, right? Instead of 3, 4, 5, you could have 6, 8, 10, or 9, 12, 15, or for that matter, 30, 40, 50, or 300, 400, 500. So there are infinitely many Pythagorean triples just by considering multiples of these. But even if you disregard those multiple situations, there are infinitely many primitive Pythagorean triples where there are no common factors besides plus or minus 1. Now, these are the three most famous Pythagorean triples. There are less famous ones. 7, 4, 25, 9, 40, 41. Those are probably the next two nice ones. Again, there are infinitely many primitive Pythagorean triples. We have three that are really nice. And on the SATs, they'd expect you to remember these. These are two pretty nice ones, but you wouldn't be expected to remember these. And again, there are infinitely many other primitive Pythagorean triples. And you can always make more by taking multiples, like 6, 8, 10, or 30, 40, 50, and so forth. Again, warning, remember the hypotenuse must be the longest side. So the missing number is not just the missing side. Okay, don't just do that. The hypotenuse must be the longest side. What I mentioned before with 3, 4, 5, 6, 8, 10, and 9, 12, 15, and 30, 40, 50, these are examples of similar triangles. Triangles that have the same shape, but maybe not the same size. Okay, so for example, if this is a 3, 4, 5, then maybe this is a 6, 8, 10, same shape but different size, and so forth. They're like nested triangles. Now, one nice thing about these similar triangles is that their corresponding side lengths are in the same proportion, and they have the same angles. And these angles will have the same sine value, cosine value, and so forth. Okay, so if you know these primitive Pythagorean triples and their multiples, the fact that multiples will work, if you know these primitive Pythagorean triples and their multiples, then that helps you work out the missing sides for these right triangles. Otherwise, you pretty much have to crank through this. Again, if the 3 were here and the 4 were here, you'd have to work through this thing. Finally, in our next video, we're going to get an example where we will apply the Pythagorean theorem and we'll revisit Sohcahtoa and the reciprocal identities and the quotient identities. Until then.